And I'd say it's all about carbon compounds and everything, all complex organisms, structures in this universe are made from carbon. Why? Because carbon makes 4 really strong bonds. So you need an atom that makes a lot of bonds if you want to make a complex structure, like the human ear or the red blood cell or the human skin. You need a complex structure. You need an atom that makes a lot of bonds. That's the first thing. And then you should know how to draw correct structures, which is that anything that's in group 4, usually most of the time it makes 4 bonds. Group 5, most of the time it makes 3 bonds. Group 6 would make 2 bonds, and group 7 would make just 1 bond. So we did structural formulas that you can make any molecule, and there's so many molecules that are organic that you can call, I mean, there's an infinite number of organic molecules. Just in the human body, there are infinite number of different organic molecules. So the thing is that all you have to make sure is that every element is making the right number of bonds. So if you've got carbon, carbon is supposed to make 4 bonds. So it is making 4 bonds. If you've got nitrogen, nitrogen is supposed to make 3 bonds. If you've got carbon over here, that should make 4 bonds. So you can have a look at this structure. Oxygen should make 2 bonds because it's in group 6. So oxygen should be making 2 bonds, and so on. So chlorine, which is in group 7, should be making 1 bond. It is making exactly 1 bond. So you need to, every atom should make the right number of bonds. That's the first thing. Carbon over here is making 4 bonds. Carbon is making 4 bonds. So every atom is making the right number of bonds. So the first thing is you should learn how to draw correct structures. That's the first very basic thing. अब उसके बाद ये कि once you have figured that out, we started doing isomers. So we started talking about isomers are molecules that have the same molecular formula, which means that they have exactly the same number of atoms, but they have different structural formulas, like, which means that they are bonded to each other in a different way. So I gave you this example, like I've got 2 carbons, 4 hydrogens, and 2 oxygens. So there could be a number of ways that these atoms could be bonded to each other. Each one of the structures is correct. Everywhere carbon is making 4 bonds. Look at any carbon it's making. All of them are making 4 bonds. All the oxygens are making 2 bonds. Everywhere you see oxygen is making 2 bonds. So the thing is, that's what an isomer is. These are all isomers of each other. You have the same molecular formula. They have the same number of atoms, but all of them have different structural arrangement or structural formulas. Now that was what isomers are. And I gave you an idea of why isomers are important in the first place. I told you that whenever you study organic molecules, because we are studying organic molecules a lot of times, because like even if you go for a simple blood test, I mean, they're basically trying to identify the organic molecules that are in your blood stream. So the very first information that anyone gets is the formula of the molecule. How many carbons it's got, how many hydrogens it's got, how many oxygens it's got. So that's the very first basic information that you receive about a molecule. And based on that, you start building a hypothesis, like what does this molecule look like? So it could look like any of these molecules over here. All of them represent the same molecular formula. So that's the first basic idea when you try to analyze a molecule. So you need to build isomers. You need to analyze it. You'll try and figure out like how many different ways could 2 carbons and 2 oxygens and 4 hydrogens, how many different ways can they exist in? And then based on that, you can do further tests and identify which one out of these structures is the right one. But anyways, we learned how to make the isomers. And I told you that if you want to make an isomer, it should have the same number of atoms. One thing that you could do is you can change the carbon chain. So instead of having 5 carbon atoms in a row, you can have 4 carbon atoms in a row and put a branch. 1 carbon atom would be coming out of that main chain like a branch, like a tree branch. Okay, so for example, you've got 5 carbon atoms. The 5 carbon atoms could be arranged in this manner, or they could be arranged in this manner. So you can change the arrangement of the carbon chain. That's one thing. Or you can change the position of a certain group. For example, you had this molecule. So instead of having C-double bond over here, I put the C-double bond right in the middle. That's another thing you could have done. So these are all isomers. Now, one thing that the answers that you sent me, one thing that was wrong was I gave you this question. Now, pretty much everyone made this mistake. Okay, that mistake needs to be corrected. And that mistake is that, remember this, and I'm going to add it over here. So remember this, that bending a molecule, rotating it around, making it upside down, I mean, these versions are basically the same molecule. So they're all the same molecule. I'll show you how. For example, I mean, this is something that you have to learn. So for example, I've got this molecule. And there is double bond O. And O and H. So here's one version of the molecule. And you can see that I've drawn a correct structure. It's got 4 bonds. This other carbon atom next to that also has 4 bonds. The oxygen is making a double bond. This oxygen is also making 2 bonds. So that's a correct. So that is a correct structure. What I'm trying to tell you is that if I draw a bent version of this, like let's say I draw another version, and this version is something like this. So I'm drawing another version. So it's this version. Now look at the 2 molecules very carefully. These 2 molecules are exactly the same. I mean, they look different, but they're just twisted versions of the same thing. I mean, like if you have a toy and you just twist it around, for example, you've got a robot and you're twisting the arms. Sometimes the hand is pointing upwards, it's pointing to the side, but it's the same robot, right? So the molecule kind of looks, I mean, these 2 molecules are exactly the same. You can start tracing it. They're both connected in the same way. The only thing is you've just twisted it around. Look at this carbon atom. I'm going to highlight this carbon atom. The first one, let's start. So let's start with this carbon atom. So I've got this carbon atom, I've got this carbon atom. Both of them are exactly the same. This carbon is bonded to 3 hydrogens. This carbon is also bonded to 3 hydrogen atoms. And then this carbon atom, next door there's a carbon which is serial bond O. This carbon atom, next door there's another carbon. And that one is also serial bond O, right? And on the same carbon atom, there's an OH attached. On the same carbon atom over here, there's an O and H atom attached. So these 2 are structurally, they're exactly the same. I mean, there is no difference between them. It's the exact same molecule. Okay? So for example, if there's a person standing or sitting, it's basically the same person. It's not 2 different. I mean, there's a bent version of a person who's standing up. If he's sitting down, I mean, you can twist them around, but it's basically the same thing. Is this point clear? Clear है सारों को? Hamza, is this clear? Saneem, is this clear? Minahil? Zainab?
Yes, sir.
Yes, sir.
Achha, so you have to be careful about that. That bending, rotating, an upside down version, or we can add to this like if you twist the molecule anywhere around, that's basically the same thing. It's not a different thing. Okay, so you can kind of twist it around. So twisted versions are kind of exactly the same. So I'm going to try the first one. Okay, now I'm going to try. Now, a lot of you, what you did was like, so I'm going to draw some right ones and some wrong ones. Like, so remember, for the structure to be different, the atoms must be arranged in a different way. So for example, I'm going to take this molecule and I'm going to draw two isomers. One of them is correct, the other one is wrong. So this is one. Remember, this is ONH. And this is H. And we can add 3 hydrogens with this. So that's one molecule. And I've got another molecule which looks like this. It's got carbon. So now what you have to do is you have to spot which one is an isomer, like a different structural formula, and which one is exactly the same formula, like the structural formula is also the same. So out of the two, I've drawn 2 molecules. I mean, I want to make an isomer of this. Basically, I want to make a different arrangement of the same atoms. So which one is correct? Is this an isomer or is this other one the isomer? Any one? A or B? Let's call this A. And let's call this one as B. Any guesses?
Sir, B.
Who's the isomer? B is the isomer. Anyone else? Saneem, any idea?
I think B.
I mean, B looks very different from what this molecule is. But the thing is that B is not an isomer. B is exactly the same thing. It's just a twisted version of the same molecule where I did not change the arrangement at all. It's exactly the same molecule. I mean, start connecting the dots. Let's start with this carbon atom over here. This one over here. This is the same carbon atom. I mean, both carbon atoms, no difference. This carbon is bonded to what? 2 hydrogens. It is bonded to 2 hydrogens. This carbon atom is also bonded to 2 hydrogens, and it's bonded to an O and H. This one is also bonded to an O and H. Hamza, Salim, is this clear? That, I mean, at least this part is exactly the same. What comes after that? I mean, after that, you get another carbon atom. So what is this carbon atom connected to? It's connected to 2 hydrogens. What comes after this? You get another carbon atom that is also connected to 2 hydrogens. What comes after that? You got another carbon atom which is connected to 2 hydrogens. What do you get after this? You again get a carbon atom that is connected to 2 hydrogens. And what comes after that? You get a carbon that's connected to 3 hydrogens. Over here, what do you get after this? You get another carbon that's connected to 3 hydrogens as well. So this one is exactly the same as this one. I mean, both of them, they don't have, the only thing is I've just bent it around and twisted it around. That's it. I mean, I haven't changed the arrangement of the atoms. The atoms are arranged in exactly the same manner. This carbon and this carbon, they're bonded to exactly the same atoms. The next carbon and this carbon, they're bonded to exactly the same atoms. This one and this one, they're bonded to exactly the same atoms. And the same goes for the last one. ठीक है, ये सारा clear है? Yes or no? Is this clear?
Yes.
अच्छा, और दूसरा क्या होगा? These are different. Can anyone spot what's the difference? Like, how did I know that these two are different?
Sir, there's 2 molecules, 3 H's.
नहीं, उसमें ना ये देख लो कि Where's the O attached? It's right at the end of the chain, like first, second, third, and it's attached on the fourth carbon atom, right? Where do you have O over here? Like if I have 4 carbon atoms, that's 1, 2, 3, and 4. So where's the O attached? It's attached on the
Third carbon.
on the third carbon. So that is clearly so that one is clearly different. Okay. Let's just a second. Hamza, did you join?
Yes, sir.
Acha. So you have to be careful with this, okay? Make sure it is a different structure, because most people, what they get wrong is that they keep on drawing the same thing. So so remember, I'm going to start all over again, okay? So make sure you remember this, that drawing a bent, a rotated upside down version, or just a twisted version of the same molecule without changing the arrangement is not an isomer. It's the same molecule. These two molecules are exactly the same molecules. They have exactly the same arrangement of the atoms. The only thing is you've just twisted it around. That's it. So what did I tell you about this? Most of the answers that I got yesterday, they had the same problem. So what you're going to do is you're going to do two simple things. One is either change the carbon chain. So instead of having 4 carbon atoms in a row, what you can have is you can have 3 carbon atoms in a row, and from the middle there could be a 4th carbon atom, and you can add the OH. And the H atoms. So that is one thing. The other thing that you could do is you can change the position of something like the OH group. You can change the position, put it somewhere else. Like you can do it over here. Like the OH is right at the end. So what I can do is I can have another molecule, because remember the arrangement has to change. So I can put the OH group over here. And the structure at all costs needs to be the correct structure. So it needs to be the correct structure at all cost. So that's another one. So remember, you have to change the arrangement. What about this one? You can do a couple of things with this, and that is that I mean, you can change the position of two things. Like if I want to draw the isomer of this, what I can do is I can have another molecule. Either I can change the carbon chain, or I can change the position of some group. Like the NH2 is right now attached over here, so I can switch it around. Because I need to change the arrangement. So I can do is one simple step I can do is yes.
If something has a double bond in like the original molecule, will the isomers also need a double bond somewhere?
No. I mean, you can do anything as long as the arrangement is different.
Okay, sir. So if the original molecule doesn't have a double bond, we can put the double bond in the isomer.
But the thing is, it would be, you have to make sure that it has the same number of atoms and it is structurally correct.
Okay, sir.
For example, I think I'll give you an example for that. Actually, that's one simple thing you could do. You can change the position of the double bond. I can put it somewhere else. For example, what you can do is the double bond is right now at this point. So I'm going to remove it from there, and I'm going to put the double bond or add it over here. Now, when I add it over here, the nitrogen gets too many bonds, and the hydrogen carbon also gets too many bonds, right? So I remove those and I complete the hydrogens over here. So again, it's exactly the same number of atoms, and it is structurally correct. So I could do that as well, or I can switch the double bond position anywhere I like. So instead of it being at the end, what I can do is I can have it somewhere in the middle. So I can have it over here, remove it from this side. And if I do that, this carbon has too many H atoms, so I'll get rid of those H. This carbon is short of one H, so I'm going to put an H over there. So even that is an isomer. But all of these are structurally different. I mean, the arrangement is different. This one had a double bond here. This one has a double bond here. This one has, this one has NH2 on this carbon atom. This one has NH2 at the end. Whereas this one has a double bond at a different position. So all of them are structurally different. So just make sure that when you make isomers, just don't make this mistake. Don't keep drawing the same molecule and thinking that they are different molecules. So these two, you have to be careful with this. These two are exactly the same molecule. So then you can also have, so what you can also have is, one second. So what you can also have is, ये जो हमजा वाली बात है कि let's say I have this molecule. This is, and I want to make an isomer of this. So I need to have the same number of atoms, but I need to change the structure somehow. ठीक है, मैं कल promise I'll start at 5. ठीक है, I'll message in the group. ठीक है. So I've got this molecule and I want to make an isomer. So remember, it's not necessary that the other arrangement has a double bond. So for example, if I have the 4 carbon atoms in a row in a cyclic structure, each carbon should be making 4 bonds. So I got H. So what you can see is that this molecule is structurally correct. Each one is making the right number of bonds. This one is C4H8. This one over here is also C4 and H8. So both of them are C4 H8 molecules. But obviously this one is harder to figure out. What you could have done is, the easiest is just alter the carbon chain. 4 carbon atoms, just alter it, or change the position of the double bond. Instead of being in the middle, you can put it on the side. That's the easier part. Drawing isomers like this is kind of slightly harder. So remember, we did some difficult examples, but for you, most of the questions would be kind of simple. You have to be creative, like 2 carbon atoms, 2 oxygens, 4 hydrogens. They could be arranged in many, many different ways, but these are harder to figure out. For you, most of the questions would be very straightforward, very simple. You can either change the carbon chain, that's it, or you can change the position of a certain group in the molecule. ठीक है, is this clear? Amna, is this clear? So then we have the next thing, which is we're going to talk about. So now what we're going to talk about is that organic compounds, there are infinite number of organic compounds. Okay, everywhere there are carbon compounds, all living organisms, every molecule in the human body, that's an organic compound. So So you need a classification system. And that classification system is known as a homologous series. Because any molecule that you draw randomly, that might exist in nature. So there's a classification system that is known as the homologous series. It's a classification system. Just like the animal kingdom, you have lots of animals. So what do? You start classifying them based on their properties. Like if you classify them as birds, they would have certain properties that they lay eggs, they have feathers, they fly, they have beaks. I mean, so you can classify them according to their properties. So because there's so many organic molecules, so you need a classification system. So it's a homologous series, just like the animal kingdom, is a family of organic compounds. So it's a family of organic compounds. Just hold on 1 second. The board has. Just 1 second. Let the board function. That's all I get. So it's a family of organic compounds having what? Having certain properties that are common to them. So if there's certain properties that are common to them, you put them in one family. Just like you classify reptiles, mammals, birds, etc. So the same way you classify them according to classify organic compounds according to these properties. So they're having similar chemical properties. So they have they show trends. They show trends in physical properties. As they show trends in physical properties, the other thing is that they have kind of similar chemical properties. Remember, physical properties are not always exactly the same, but they would show trends in physical properties. Like they have low melting points. I mean, the melting points are not going to be exactly the same, but if they have low melting points, then all of them are going to have low melting points. Not exactly the same, but they would have low melting points. They have the same functional group. What that means is that they have a certain functional group is a structure or group of atoms in a molecule and it's a structure or group of atoms in a molecule that determines its chemical as well as sometimes the physical properties as well. whether they're going to conduct electricity or not, physical properties. So it's the structure of group of atoms in a molecule that determines its chemical and sometimes physical properties. So what I mean by this is most organic molecules are a bunch of carbon atoms and hydrogen atoms, but they have certain groups in them. Like there's an OH group and O and H bonded together. Now this molecule, most of its reactions and most of its physical properties are because of this OH group, right? Like the rest of the molecule doesn't really do much. The things that are reacting are this part. This is the part that is reacting. Like if you, I mean, look at any organic molecule. Let's look at a very complicated organic molecule like the human skin. I mean, not the whole human skin is always reacting. The human skin has certain areas which are more active, like it's got pores in it, where chemical reactions happen. Okay, so organic molecules are large. Not the whole thing is basically reactive. Most of the time, this carbon chain is kind of very unreactive. Okay, so it's not taking part in the reaction. It's only certain groups in the molecule that are actually actively taking part in the reaction. Is this point clear? Yes or no? Is this clear? Hamza, is this clear? Saneem, is this clear?
Yes, sir.
So I'll give you an idea. Like we did, if I can find this. So wanted to show you certain reactions. Just a second. So for example, that's too complicated for you. Just a second. Acidification, alcohol. So for example, this might. So for example, this part. For example, you have in which, so it's not the whole molecule. Remember R, very often in organic molecules, the term R is used. R is used as the rest of the molecule. Like a lot of times this is used. Like, I mean, this part is not reacting, so you just call it R. R just means the rest of the molecule. So the point I'm trying to make is that a lot of times it's certain groups in the molecule that are reacting, that are taking part in the reaction, like the H and OH they combine to form water molecules. I mean, the rest of the molecule is not taking part in the reaction. So that's the whole point, that that's known as a functional group. Not the whole molecule will react, only certain portions of the molecule will react. The same goes for these molecules. Like if you look at this molecule, the whole entire molecule is not going to take part in the reaction. It's going to be, I mean, most of the time it's this double bond that actually takes part in the reaction. Okay, so you've got all these functional groups. Like over here, you've got two functional groups. You got this double bond that takes part in the reaction with certain substances, and you've got this NH2 group. I said no one pointed this out. What is structurally incorrect with this molecule, this entire molecule?
It's bonded 4 times.
It should not be bonded to four times. It should be making just 3 bonds. So we didn't spot that. Did I?
And so another thing, will there ever be a question where they give you a question, they give you incorrect bonds and they ask for isomer of that? Or will the actual molecule always be correctly bonded?
No, remember the first thing is just like a formula, a molecule has to be drawn correctly.
Okay.
I mean, like if whenever you hear the term sulfuric acid, it's always H2SO4. So
Yes, sir.
whenever you draw the structural formula, it always has to be the correct version. You can't draw the incorrect version. Okay. So this is what a functional group is. So when you see these molecules, you're going to put them in the same functional group. Like any molecule that has a double bond, you put them in the same functional group because they're going to react in the same way. Any molecule that has NH2 groups, you put them in the same family of organic compounds because they're going to take part in the reaction in the same way. So remember, these are the three main properties. Like, how do you classify organic compounds? They're supposed to show similar chemical properties, and they're supposed to show similar physical properties. And the reason they have similar chemical and physical properties are because they have the same functional group as well. So you classify them in the same family of compounds. Okay. So let's continue with this in the next class then. Okay. Okay, everyone.
Yes, sir.
Take care. Allah Hafiz.